Alright, this is part 2 of our electric potentials. So I have a charge on the right, it's going to be anchored, and I have a charge on the left moving towards it with a certain amount of initial kinetic energy. As it moves towards the charge on the right, it's going to be repelled because they're the same sign. And so I'm going to lose kinetic energy as it moves towards it. And when I lose kinetic energy, that energy has to go somewhere, and that energy is going into the actual field. So what we do when we look at this, we look at this as potentials. The line, each one of these circles, they all has the same potential. So the one that says positive 182 V, that's volts, that potential is the same everywhere on that line. Plus 92 V, that's plus 92 volts, that's the same everywhere on that line. So these are equipotential lines. As the charge moves towards it, as one charge moves towards the other, it's going to lose kinetic energy because they're repelled, and that energy is going to go to the electric field, so potential energy will be gained as kinetic energy gets lost. So what happens if I change the charge to a negative sign? Well, with gravitational potentials, I didn't have to worry about this, but with electric potentials, I do have to consider it. So these two charges are attracted. So this time, instead of losing kinetic energy, I'm going to gain kinetic energy. So it's going to go faster and faster as I move towards the negative charge. But the potentials here are different. With a negative charge, instead of having positive potentials, I'll have negative potentials. So as I get closer and closer to the negative charge, it becomes more and more negative. So as a charge moves across potentials and it goes to a lower potential, and negative 182 is lower than negative 45, think of it as a number line, so I'm moving farther away from zero, which makes it lower. As it decreases potential, it increases kinetic energy. The same thing was true about the last example. As I moved out, the potential got weaker and weaker. So it's still true. As I move to a lower potential, I gain kinetic energy. So if I look at it in terms of a graph, the kinetic energy as I move towards a particle is going to increase, and the potential energy from the field is going to decrease. Okay, let's take a little note about the electric potential lines. My white vectors, they're going to be the E fields. My green lines are equipotential lines. Notice something about the white vectors. They're all perpendicular to the green lines. So the E field vectors are always going to be perpendicular to our equipotential lines. Here's another one. It's got a little different shape to it. Still true, the vectors are still perpendicular to the electric potential lines. We have these things called equipotential surfaces. If I bring a charge device, such as a Tesla coil, and put the charges on the actual metal spheres that I have here, I'll have an infinite number of equipotential lines. Well, if I have an infinite number of equipotential lines, this basically forms what's called an equipotential surface. So everything on the surface has the same potential no matter what the shape of it is.